Okay, so our next topic. Okay, so this would be about helical springs. Okay, so by definition, so we have here a helical spring, no? So this is type of spring composed of wire or wound, wire or round rod of diameter d. So wound into a helix of mean radius r. So basically, so the helical spring, no? So can experience also stress. So the stress, no, of a helical spring, stress developed, no, in a helical spring uh, can be approximated using the first formula. Okay, this one. So this is an approximate, no, so approximate formula. So the 16 times the, okay, so 16 times the applied force, and then R is actually this the radius, no, of the spring. For example, this is spring. So the radius R is the radius, no, so that is the radius of the spring. And D, the small letter D, that is the cross-sectional area, no? So this is the cross-sectional area of the uh, rod or wire. So the spring material, okay? So do not be confused with R and D. So D is the cross-sectional area, no, of the rod or the spring material, whereas R is the radius of the spring. Okay, so sometimes the approximate formula may not give, no, so the exact result, no, of the spring. So because this is only intended for light springs. Okay, so when you say light spring, so the ratio D over 4R is very small. So if you cannot find the answer, okay, so there is uh, okay, so there is a more precise formula in calculating for the stress of a spring. So that is using the heavy spring formula. So as you all know, so we consider the what we so called spring factor M. Okay, so we term M as a spring factor. So M that is equal to 2R over D. So this is the spring factor, and we consider the expression m minus 1 over m minus 4 as to be, that is the what we so called uh, wall factor. Okay, so normally we try, no, so the best step is to memorize, no, all the formulas, but uh, for simplicity, so we may try to memorize the light spring formula because this is very short. So the difference, no, so the difference between this light spring and the heavy spring formula as a result, perhaps they may be, or the difference, no, is big. Okay, so if that's the case, particularly you can't find the answer, no, from the multiple choices, then it is best to use, no, the heavy spring formula. And the elongation, no? So the elongation for helical spring is given by this formula. Okay, so we have the representation of the variables: the spring, shearing stress, elongation, applied force, mean radius of the spring, diameter of the wire. So N stands for number of turns, modulus of rigidity for the variable, G. Okay, so okay. So now we proceed no, to example number 13. Okay, for as an example no, for helical spring. Okay, so in example number 13, so you have there determine the elongation in the helical spring. So composed of 20 turns of 20 mm diameter wire. So 20 mm here refers to the uh, variable D. So the mean radius is 80 mm. So this is the variable R. So when the spring is supporting a load of 2 kilonewtons. So use the modulus of rigidity equals to 83 gigapascal. Okay, so we proceed no to item number. Okay, so this is just a calculation no for the elongation no of the spring. So the elongation of the spring that is given by the formula. Okay, divided by the uh, GD4. Okay. So one calculation, so we can calculate directly now 64 times the applied force, that's or the load, no? So that's 2 kilonewton. The mean radius is 80 mm. Number of turns 20. So G there is 83 gigapascal. Okay, so then diameter is okay, 20 mm. So this is 80 by the way. So 20 mm. So the elongation would be so you have there the elongation of 0.987 or 0.0. Okay, so that's 0.0987 meter. Okay, so that's basically that is equal to 98.7 mm. So as to the stress, so since it's not asked now, so let us try to compare the. So by the way, this is the answer now. So we try to calculate for the stress. Okay, so the stress in the helical spring using the approximate formula. So we have there the. So let us just consider now. So the approximate formula and also the heavy spring formula. No? So which uh, we will try to observe the difference no, in the stress. So this is 16. So that is 2016 PR divided by okay, so pi times 20 mm cube. Okay, so multiplied with 1 plus D, okay, over 4 times R. So this is the approximate formula. So we'll just, so it's not part of the solution. No? So we are just showing here the difference between, okay, so multiplied by, okay, so using the approximate formula, so you have there the stress of 108.2 megapascal. Okay, so but using the uh, heavy spring formula, so you have the 16. So this is the same as with the light spring. Pi cube. So this should be uh, multiplied. So m is equal to 2r over d. No? So this would be 2 times 80 divided by, okay, so this would be 8. So we have here 8 minus 1. Okay, and then uh, 8 minus 4 plus 0.615 over 8. So the stress, no? So using the, okay, so that's, so 7 divided by 4 plus, okay, so using the, okay, so we can have the formula, no? So the difference is 186, or the answer is 186 uh, megapascal. So you see the difference, no, between the two. So uh, it would be better, no, depending on the choices presented. So you can use the approximate formula or the okay, so the heavy spring formula. Okay, so for okay, so to solve for the unknown, no, but for this item, so the answer is 98.7 mm, which is the elongation. Okay, so we now proceed, no, so with the last topic. Okay, so which is the stresses, no, stresses or stress in beams. Okay, so we run through, no, so the following formulas. Okay, and then the method in solving will be presented using the 3 sample problems. Okay, so we have here the maximum shearing stress or maximum shear stress, no? So the maximum shear stress, so this is given, so depending on the cross-sectional section, so you have there 3V over 2A. No? So V is the maximum shear force in the beam. So by the way, so there may be some variables no, that is different from the variables presented in books. Okay, so uh, just refer to the uh, variable name as to which the variable is presented in the formulas. For example, V here, so this stands for maximum shear force. Okay, and then S max, so this is the maximum shear stress. Okay, for cross-sectional section, so you have the 4V over 3A, and then we have the maximum bending stress or the flexural stress. Okay, so we have here SB max, no? So which is equivalent to MC over I. So first M here, M stands for the maximum moment in the beam. Okay, so this is the maximum value of the moment in the beam. C represents the distance of the neutral to the extreme fiber, no? So this is from the neutral axis to the top or bottom of the beam, no, or the surface. Okay, so I, of course, is the moment of inertia. So we just have the two formulas for rectangular and cross-sectional, rectangular and circular cross-section. So there may be other formulas, no? So depending on the type of cross-section. But in most cases, the commonly used cross-sectional area for beams are the rectangular cross-section and the circular cross-section. Okay, so we just go over with the formulas later again. Okay, and then the process in calculating will be shown in the sample problems presented. Okay, so in the item number 14, so we are asked to determine the maximum moment of the beam. So if we try to look at, so the maximum moment is given by B, I mean the variable M. Okay, so we will be creating in item number 14 the okay, the moment diagram so of the beam. Okay, so we will be showing. Okay, so this would be for problem number 14. So for problem number 14, so we are given with a beam. Okay, so this would be the beam. The supports are given to be R1, R2, and uh, a concentrated load of 100 kilonewton and another concentrated load of 200 kilonewton. So the distance is 5, also 5 meters here, and we have 10 meters. Okay, so the first step now in calculating is to calculate for the uh, support, no? So R1 and R2. So first is we do uh, summation of moment at B. Okay, so summation of moment at B, so that is equal to 0. Okay, so we have here R1 multiplied by 10. No? So R1 multiplied by the distance 20. Okay, so that is minus 100 kilonewton multiplied by the distance to point B is 15 minus 200 kilonewton multiplied by the distance to B, that is 10. That is equal to 0. So calculating R1, so you have there so R1 then is equal to 175 kilonewton. And then we do summation of moment at A. So we have here variable A. So we have there, okay. So we have there R2 multiplied by 20. So negative, no? Plus, okay, so that is 100 multiplied by 5 and plus 200 multiplied by 10. So that is equal to 0. And then you have there R2. So R2 then is equal to 125 kilonewton. Okay. So now we write the shear diagram first. Okay. So the shear diagram will correspond to the okay. So first is R1. So R1 is given to be 175 kilonewton. So with respect to this reference line, so you go upward. So this is 175 kilonewton. So no forces in between. Okay, so you go straight, okay, up to the next force. Okay, and then 100 kilonewton is pointing downward, so that's 100. So this will have a remaining value of 25 kilonewton. So 175 minus 75, that's okay, so this is 25. And then, okay, so no forces in between, so you go straight until the next. Then you go downward again with 200 kilonewton. Oh, sorry, we have here 75. Okay, sorry, this is 75. So 100 minus so this is 75. So this is actually 175 minus 100. Okay. So this is 75. So subtracted with 200. So you have there 125. Of course, negative. That means it's below the reference line. And then no other force in between. So go straight. And you have there R2, which is 125. Okay, so upward, so it goes back to 0. So you will know that you will have or you have the wrong answer because the closing point is not equal to 0. Okay, so this would be the 125. No, so from the formula, so this is the okay. That's the um, okay. So this is the maximum. If you try to look at the formula presented a while ago, so we can then say that the maximum shear force is equal to. So you just look at the maximum or the highest value. So that is the 175 kilo Newton. Okay. So this is the maximum shear force, no, from the shear diagram. So now we go to the moment diagram. Okay, so the moment diagram would be equal to, okay, so again we have the reference line. So in the moment diagram, so you start with, okay, so you start with, okay, so this is the moment. In the moment diagram, you start with 0. Okay, so let you look at, you start with 0. Okay, so then we consider the area of this first uh, section. So area of the first section, okay, area is equal to, so that is 175 times 5. So since this is rectangular, no? So this is equivalent to 175 times 5. So that is 875. So you draw a straight line, so going upward. So this is okay. So you draw a straight line. So this will have a value of 875. Okay. And next is you have to consider the area here, the second section. So area is 75 multiplied by 5. Now, so that is equal to 375. So you add 375 to the existing value. So 875 plus 375, that is equal to 1,250. So you go there, so that's 1,250. And then considering the fourth area, cross section, this one, okay. So area here would be equal to 125 multiplied by 10. Okay, so the length is 10. So you have there 1 to 50. So since this is located at the bottom, so this point here will be subtracted by this area. So 1 to 50 minus the area at the below the reference line. So this would be equal to 0. Okay, so again, you will know that you got the wrong solution because you will not end up with 0. So if you try to look at the maximum moment, no, so in the beam is given by, so just try to look at the maximum or the highest value, that's 1 to 50 kilonewton meter. So do not forget that we're using kilonewton, no, as the base unit for the force. So therefore, the unit is kilonewton meter. Okay, so we call this one the stress diagram, the moment diagram. Okay, so That is for item number 14. No? So just try to look at item number 14, try to look at the solution, I mean the choices. No? So that's 1 to 50. So you have it letter C. Okay. And we go to, no? So we go to number, okay, so we go to number 15. Okay. So number 15, so we're given with the beam, no? So shown, so 5 inches wide and 10 inches deep. So this means that it has a rectangular section. So what are the maximum bending and shearing stress? So we're asked to calculate, no, for the maximum shearing stress. Of course, this one. So rectangular cross section, and then the bending stress. So the bending stress is given by this formula MC over I. No? So first is we need to draw the moment shear and moment diagram. Okay, so okay, so we have the okay given in number 15. So we are given with, no, so the beam, so it supports R1 and R2, and so we are given with, okay, so I uniformly distributed load of, okay, so that's 300 pound per foot. Okay, so this would be 14 feet, and we're given with 300 pound per foot, and also, okay, so that's the this would be 6 feet. So first is we need to calculate for the support, no? So to okay, so to analyze it simpler, so we can represent, no, the uniformly distributed load with its equivalent concentrated load. So this would be R1, this would be R2, and then this would be 6 feet here. So it would be represented by uh, a concentrated load of 300 times 14. So wherein the distance here is 7, and also you have the 7 feet. Okay, so such that if we uh, sum up moment, no, so this would be, let's say, moment point B. So if we do summation of moment at B, so that is equal to 0, so that's 300, no, times 14, so that is equal to R1 multiplied by 20. So R1 then is equal to, so this is 210. Okay, and then Likewise, if we do summation of moment at A, so that is so assuming this is point A, so you have there 300 times 13. Okay, so that is equal to R2 multiplied by 20. So R2 then can be calculated by, okay, so divided by 20. So you have there 195. Okay, so 300 times 14 is, okay. So 300 times 14, sorry, we lock, no? So we are locking with the distance, no? So this is 300 times 14 is still it's the equivalent force, so it should be multiplied with the distance, no? So that's, so 300 times 14 multiplied by the distance 7. So 300 times 14 times 7 divided by 20. So this would be 1470. And then on the other hand, so this should be multiplied with the force 300 times 14 times 13. Okay, so 300 times 14 times 13 divided by 20. So this will be equal to 2730. Okay, so the next thing to do is to draw the shear diagram. Okay, so for the shear diagram, so we start by writing, no? So in this section, so you have R1. So R1 going upward. So this is 1470. So no force in between until this section. Okay. So you have there 1470. Okay. So now for the cross-sectional or the horizontal distributed load, so you start by having 1470 and then try to consider the area. Okay, so the area here, so that is um, area that is um, 300 multiplied by 14. Okay, so that is equivalent to 4,200. Okay, so 1,470 minus 4,200. So you will have, or you will end up with, so since there are no forces in between except for the distributed load, so all you need to do is to subtract it directly. So you will end up with, okay, so this is 1,470, so minus the area, okay, so you will end up to this point at, okay, so this is equivalent to uh, this point here, so this is equivalent to 1,470 minus 4,200. Okay, so this is equal to, so negative 2730. Okay, then you have the R2 pointing upward, so which is also equal to 2730. So you will have, or it will be close to 0. Okay, so next is to identify, no, the um, moment diagram. Okay, so for the moment diagram, you look at the shear diagram, no? So this will be the first section. This would be the second section, and then it crosses zero here, no? So this is the third section, and of course this is the fourth section. Okay, so you start with zero, and then you consider this area, the first section, no? Okay, so area here, so that is equal to 1470 multiplied by 6. So this would be 8820. So 0 plus 8820. Okay, so you may have also this reference or straight line. So this is 8820. And then you consider the second section area, this one. So area here, so this is a triangle 1/2 base. So this would be x, and then the height is 1470. So let's just use b, base, and then the height 1470. So as to the base, we do not know the length because 14 is the length, no, from this point to this point. So to calculate b, so all we need to do is to go back, no? How did we get this equation, no? So take note, this is 1470. So we start by this point, no? So that's 1470 minus the area, no? So covered up to this point, this one. So this is with B. So minus, so the area of the shaded portion, no? So that's 300 multiplied by B. The resulting answer is 0, no? Since we have 0 shear force. B then can be calculated as, okay, divided by 300. So that's 4.9. Okay. So if this is 4.9, so this is also equivalent to 9.1, and this would be 4.9. Okay. So area here can be calculated by 1/2 times 4.9 times 1470. So you have there 3601.5. So you add. So this is triangular form, so it has to look like this one, no? It somehow bends. So anyway, the formation does not matter. What matters most is the point, no? So to where it ends, no? So this point here is equal to 8820 plus 3601.5. So 8820 plus 3601.5. So that's 12,421.5. Okay. So that's 12,421.5. So 12,421.5. And then next is you have to consider this area. Okay, so area here is equal to 1/2. Base is 9.1 and the height is 2730. So this would be 12,421.5. 421.5. So if you try to look at, so this is pointing, okay. So you have to subtract, no? 12,421.5 minus this one. So it ends with 0, no? So you will have this one, okay, 0. So as again, you will know that you have the wrong answer because of you will not end up with 0. Okay, so we are now ready to calculate, no, for the maximum shearing stress. Might as well the, okay, so maximum, okay, so you have the maximum bending and shearing stress, no? For the maximum shearing stress, okay, so that's, okay, so S max, that is equal to 3V over 2A. So V, so if you try to look at V here, is the maximum force, no? So which is actually 2730. So although it's located at the bottom, okay, so but this is the maximum shear force, no? So, and in area, okay, so considering the area, so as given, so you have there the 5 inches and 10 inches, no? So 5, so this would be 5 over 12 feet, and this would be 10 over 12 feet. So we'll just use feet, no? Because the units of measurement is in feet. Okay, so area then is equal to 5 over 12 times 10 over 12. No? So this is equivalent to, so that's 0.3472 feet square. Okay, so calculating for the maximum shear stress, no? So that's equal to, so 3 times. So the maximum shear force is 2730. So it does not matter, no, if it is negative or positive. Okay, so negative means it's below the reference line. So 2 times area, that's 0.3472 feet square. Okay, so S max is equivalent to, okay, so that's 3 times 2730 divided by 2 times 0.3472. So unit 11794.4. So pound per feet square, no? So we have to convert it to inch, no? So or you can, that depends on you, no? So you may start with inches at first, or you may start with feet. So anyway, they will arrive at the same answer, no? So this will be multiplied with 1 foot, 12-inch square, no? So and then you will have there, okay, so you will have 81.91 psi. Okay, so for the other question, so that is the maximum bending stress, no? So maximum bending stress, that's okay. So that's we'll just delete this one. So SB max, that is MC over I. Okay, so what in M? We try to look at M. So you have there 12,400 now. And then we can start with M, no? So M is 12,421.5. Unit is foot pound. Okay, so we just convert it to inches again. So that's 12 inches per foot. Okay, so that's okay. So that's so you have there 1,409.58 unit in inch pound. So C, so obviously this is from the center to the top. So this is 5 inches. Okay, so and then I, okay, so just have it. I here is equal to 4. Okay, the rectangular cross section, so that's BH cube over 12. Okay, so just refer to the uh, part no in the recorded lecture wherein the formulas are shown. So base is 5 feet and 5 inches. Height is 10 inches divided by 12. No? So moment of inertia, that's 5 times 10. So that's 416.67 inch to the power of 4. So going back here, so we have here SB max. So that's M149058 MC 5, okay, and then divided by I. So 416.67. So SB max would be equal to, so you have there 1788.68 unit in pounds per square inch. Okay, so that would be the process, no, calculating for the maximum shearing stress, okay, and then the maximum bending stress. Okay, so for the last item, so we have the, okay, so let me share again the, okay. So just refer to the formulas, no? So presented, okay, so during the discussion, okay, so you may take them down, okay, so for you to have the formulas, okay. So the last item, no? So in example number 16, so you have there a cantilever beam, so 3 meters long, subjected to a uniform distributed load of 30 kilonewtons per meter of land. So the allowable working stress in either tension or compression is 150 megapascal. So if the cross section is to be rectangular, determine the dimension of the width. If the height is to be twice as great as the width. Okay. So okay, so you have there the allowable working stress, no? So in either tension or compression, no? So that's the okay, so that's the maximum, no? Shear stress. Okay, so that's 150 megapascal, no? So that's we are asked to uh, determine, no? So the dimension of the width. So So basically, we're given with S max, and then we are asked to obtain, no? So the width. Okay. So anyway, we need to draw, no, the shear and the moment diagram of the beam. Okay, so this is number 16. So when you say cantilever beam, so it looks like this one. Okay, so this carries a uniform distributed load of as stated, no? So that's 300. Okay, so that's 330 kilonewtons per meters. Okay, so that's 30 kilonewtons per meter. So the length is 3 meters long. So for a cantilever beam, so the support, no? So the support would be uh, this would be the support, no, for a cantilever beam. So you have there the moment. So it actually has the moment, no, at its end, and at the same time the support, no, so given by, let's say, R1. So the uniformly distributed load can be represented by a single concentrated load of 30 uh, 30 kilonewton, so multiplied with 3. So that makes it 90. So this would be 1.5 and also 1.5 here. Okay, so basically, uh, if we sum up, no, summation of forces, no, along y, so that would be 0. So obviously R1 that is equal to 90 kilo Newton. Okay, and we cannot do summation of moment here. Okay, because there is already an existing moment, so we can have point A here, and then if we do summation of moment at A, so you have there equal to 0. So moment at A, so you have there 90 multiplied by negative 90, no? So multiplied by 1.5. So negative because it's okay. It's counterclockwise direction, no? So and then plus R1, so that's R1 90. Okay, so okay, so we can okay. So instead of A, so we can have okay. Okay, so I accidentally deleted, no? So anyway, so this is the cantilever beam that we're talking about now. So that's it has the moment here, and then the uniformly distributed load, no? So the uniformly distributed load of 30 kilonewtons per meter. So, okay, by definition, so a cantilever beam, so it has the support R1, and then it has the moment now at this point. So this would be 30 kilonewtons per meter. Okay, so we can just simplify it by writing the equivalent concentrated load. So this 30 times 3, so which makes it 90. So this would be 1.5, 1.5. Okay, so you have there R1 and another moment M. Okay, so let's say we have here point A. So we can do, by the way, we can do moment here, but we have to consider now. So this moment equation, I mean moment M. Okay, so we know that if we sum up forces, so R1 would be equal to 90 kilonewtons. So just the same as presented a while ago. And then if we do summation of moment at A, no, so that is equal to 0. So the effect of R1 will be nullified now because that is at point A. So we have to consider this one. No? So that's 90 multiplied by 1.5. Okay, so moment here is also initially clockwise direction. So that's plus moment that is equal to 0. So moment at point A, so that's equivalent to negative 135 kilonewton meter. So this means since this is negative, so the direction supposedly is this one. Okay, so that's 135 kilonewton meter. Okay, so we write the shear and moment diagram. Okay, so we have to, okay, so that is for the shear. So we start with 0 and then R1. No? So R1 is 90. So this is 90. And then it will be subtracted. No? So with this area. Okay. So this area is equivalent to 30 multiplied by 3. No? So 90 minus 30 times 3. So you will end up with 0. 0. No? So this is 90 minus 30 times 3. Okay. And for the moment, okay, so for the moment, so instead of starting with 0, since we have the, okay, so since we have the moment ready, okay, you have there the moment which is 135 kilonewton meter. So you start with 135 kilonewton meter. So that's 135, okay, kilonewton meter, not 0 because a moment at this point so exists. Okay, then minus, so you have to consider this area. Okay, so the area here is 1/2, base is 3, height is 90. Okay, so area then is equal to 3 times 90, so that's 135. Okay, so that would be 135 kilonewton meter minus this area. No? So that would be equal to 0. So again, you will end up with 0 if you have the correct answer. No? So this 135 here and this one is the same. No? So whereas this one, so uh, this is the maximum moment Okay, so and then the variable M, and then this would be the maximum shear force 90. So if we try to look at the item, no, or okay, so that's 150 megapascal. So 150 megapascal, that's 3V over 2A. Okay, so okay, so we have the okay, so the maximum shear force, that is 3 times 90,000, no? Divided by 2 times area. So if you try to look at, this is the width, and then the length is said to be twice the width. Okay, area is 2W square. Okay, so calculating for the width, no? So 3 times 90,000 divided by, okay, divided by 4, square root, okay, square root of the answer. So width, that would be 0.021 meter, no? So, okay, so, okay, so determine the, okay, so that's 0.021 meters, okay? And okay, so that's let's try to look at if the answer is in the choices. So 0.021 is not enough. So in the choices, so okay. So perhaps we might consider now so the maximum bending stress. Okay, let us try. Okay, so if we consider, okay, so if we consider the maximum, okay, so SB max, so that's MC over I. Okay, so M here is 135,000. So C, so going back to, okay, so this is the width, and then this would be the height. So that's 2 times the width, no? So C is width over 2, okay? And then I is basically BH cube over 12. So base is W, height is 2W cube, okay, over 12. So we have here 135,000. Okay, then, okay, so basically we can have, okay, so that's, so 135,000 divided by 2, then divided by 2 cube over 12. Okay, so that we can have the number So that's 101. Okay. So that's 150 times 10 to the power of 6. That's 101, 250 over W square. Okay. W, okay, cube. I mean, W cube. So we can cancel out W. So with W cube remaining, no, in the denominator, so we have there 101, 250. Okay, and then take the cube root of it. So, okay, so with then is equal to 0.08 77. Basically, that's 87, no? 87.7 mm. Okay, so um, okay, so that's 150. Okay, so still we haven't have no, so the uh, answer no from the choices. Okay, so just go over now with the calculations again. So try to look at if we have some miscalculations, no? So in the process. So but the process would be this way, okay? And then out from this one, so let's say you have to consider this one and this one. Okay, so uh, to determine no, whether uh, which one is correct. Okay, so whether it's 87.7 or 0.021, so all you need to do is to substitute it, for example, in this equation. So that's 101 to 50 divided by 0.021 shift cube. Okay, so this will result to, okay, so this will result to 10,932 megapascal. So, so that means we cannot use this with, no, because it uh, the maximum bending stress will be greater than 150. So also assuming that we use no this with, okay, to this equation, so that's 3 times 90,000 divided by 4 times 0.0877 square. So this will only be around 8.78 megapascal. So of the two, so the answer is 87.7 because it passes both the bending stress and the maximum bending stress and the maximum shear stress. Okay, so I would like you to go over with the calculations. No, so perhaps we have uh, some miscalculations no, in between, but then if there are none, then the answer would be 87.7 mm. Okay, so that would be for mechanics now, deformable bodies.